This is Mr. Martin. These are video notes for Pre-Calculus Honors. We're in section 8.4. This video is going to talk about mathematical induction. So basically mathematical induction is just a method or form of proof, just like in geometry when you did two-column proofs, or you did indirect proofs, or you did paragraph proofs. Mathematical induction is just another type of proof. So the general idea behind mathematical induction is to show that the next case is true. Okay, and then the basic principle is that we're going to let P sub n be a statement involving the positive integer n. Okay, and P sub 1 is true, so we'll show that P sub 1 is true, and then the truth of P sub k will imply the truth of P sub k plus 1. So if we have some term P sub k plus 1 is really just the next term, and then we want to prove this true for every positive integer k. Alright, if we can do this, then P sub n must be true for all positive integers of n. So you'll get the idea of it after we do a couple of examples. But as always, if you have questions, make sure you write those down. Make sure you ask me them if you happen to be watching in class. So for example 1, really all we're doing is if I'm given P sub k, what is P sub k plus 1? So P sub k plus 1, we're literally just going to plug in k sub 1 for all of our variables. So we're going to have 6 over. So I have a variable here. I'm going to put in k plus 1 for that. And then I have a variable here, so I'm going to put in k sub 1 for that. So k sub 1 plus 3. And we'll do a little bit of simplifying. So I have 6 over k plus 1 times k plus 4. Sometimes we'll FOIL it out, sometimes we won't. So this is P sub k plus 1. It's the term after. This is the term after P sub k. Alright, it's just the next term. Okay, so why don't you go ahead and pause the video and see if you can find s sub k plus 1 if we're given s sub k. And in this instance, we're given it as a series instead of as just a formula. So pause the video. When you restart it, I'll have a solution for you so you can check and do that now. Alright, so a couple of things to notice first of all is that these last two terms in the series, this is s sub k minus 1, and then this would be s sub k. And what we're trying to find is we want to try and find this next term here. This next term here, this is going to be s sub k plus 1. So just like in the last example, we want to start with s sub k, which is going to be 3k minus 1, and instead of k, we're going to substitute in k plus 1. Once you do that, it's just some algebra here of distributing and combining like terms to get s sub k plus 1 is equal to 3k plus 2. Okay, so this is just kind of a warm-up to get us into the meat of the video here. We're going to use mathematical induction to prove the following formula. So what we want to show is that this sum, 1 plus 3 plus 5 plus 7, basically these are odd numbers, is really n squared. So if I wanted the sum of the first 10 odd numbers, I could just plug in 10 there to get 100, and the sum of the first 10 odd numbers should be 100. So the idea here is to prove that n squared would be actually that formula to use. So the first step here is to show that this relationship is true just for the first term. Okay? So this is what we might think of as a formula to generate the terms. So we want to see, does this work for the first term? So is 2 times 1 minus 1 equal to, notice the question mark there because we don't know if it's equal to it yet, and then 1 squared. So I plugged in 1 for n here to get the first term, and I want to see if it equals 1 squared over there. And we can see 2 minus 1 is 1, and 1 squared is 1. Okay, so that works. Okay, so basically what we did here, show that relationship is true for first term. Okay, so if it doesn't work for the first term, it's not going to work. All right, next, this is kind of a standard step here. We're going to write out assume S sub k, so if we plugged in k, is true, then what we want to do is show that S sub k plus 1 is also true. So we're going to assume that this is true for S sub k. So if I plugged in k here, we would assume that the sum of the first k terms would be k squared. And then the rest of this is going ahead and proving that. So I'm going to have 1 plus 3 plus 5 plus 7 plus all the way up to 2k minus 1. So that's the S sub k term. All of this is S sub k, but then we need to add one more term, the k plus 1 term. So plus 2 times k plus 1 minus 1. Okay, so now I put in k plus 1 for n. And we want to show, again, notice the question mark because we don't know if this is true yet, that this is equal to, and then for n, we want to prove it's true for k plus 1, k plus 1 squared. Okay, so we already figured out that all of this is S sub k, and S sub k, we're assuming that that's true, so we're assuming that's equal to k squared. Okay, so we're going to have all of this stuff. So our next step here would be that k squared from all of this stuff here, let me highlight that, all of this is k squared because we're assuming S sub k is true, plus, let's do a little simplifying here, that's going to be 2k plus 2 minus 1, so that's 2k plus 1, and we want to still figure out if this is equal to k plus 1 squared. And either way you want to do this, you could either FOIL out on the right or you could factor on the left. So let's just factor this. K squared plus 2k plus 1 is equal to k plus 1 squared is equal to k plus 1 squared. And then we just denote that we have proved it with the check mark. We assume that the S sub k term or series was true. We want to check it for S sub k plus 1, and we actually did that here. And the proof is done. So again, make sure that you ask questions. And once you do a few of these, you'll get the hang of it, but you are going to want to get a fair amount of practice doing these. So let's go and pause the video again and give this problem a try. Follow the steps that we did before. And when you're ready, you can go ahead and start the video back up and check your proof. All right, so here's the proof. Step 1. Again, we want to show that this relationship is true for the first term, so we plug in 1 to our relationship here and plug in 1 over here and make sure that those are equal, so we get 5 is equal to 5. Okay, then our standard statement, we're going to assume S sub k is true, prove S sub k is 1 plus 1 is also true. All right, so we've got our series here, 5 plus 7 plus 9 plus 11 up to 3 k plus 2. Okay, so that's up to k, and then we're going to do the k plus 1 term, so we're going to plug in k plus 1. All right, so if this was a little unclear, all of this is k plus 4, because we're assuming that k times k plus 4, that up through k, that this relationship is true. So we substitute in k here. So all of this is k times k plus 4. And then over here, I'm plugging in, substituting in k plus 1, and all of that simplifies to this. Okay, so the highlighted parts match up there. And then when we simplify here, we'll distribute and add like terms. We get k squared plus 6k plus 4. Then on the other side, I substituted in k plus 1. So here's a value of n. I plug in k plus 1. Here's another value of n. I plug in k plus 1. This simplifies to k plus 5. When I FOIL that out, I get k squared plus 6k plus 4. So it is true for the k plus 1 term, and we've proved that this formula holds true for this series. All right, and again, if you have questions, make sure that you ask. All right, let's look at one more example here. We want to prove this using mathematical induction again. So step 1, we want to show that this is true for the first term. So we want to show that 1 times 1 minus 1 is equal to 1 times 1 minus 1 times 1 plus 1 over 3. So we plug in 1 and we put on each side and double check that they're equal. So I get 1 times 0 is 0. I'm going to have a 0 in the numerator here, so that's also going to be 0, so that's true. So it's true for the first term. So then we are going to assume s sub k is true. Prove s sub k plus 1 also true. So let's go ahead and look at that. So I have 1 times 1 minus 1 plus 2 times 2 minus 1 plus all the way up to k times k minus 1. And then the next term, the k plus 1 term, so all of these spots here I'm going to plug in k plus 1. So I have k plus 1 times k plus 1 minus 1. And we want to show that that's equal to, so all of these n's we're going to plug in k plus 1. K plus 1 times k plus 1 minus 1 times k plus 1 plus 1 all over 3. We want to show that those are equal. Alright, so all of this here, this is s sub k, and we were assuming that that was true. So we're assuming that this is going to be true, so that's k times k minus 1 times k plus 1 over 3. We're just substituting in k over here because we're assuming that that is true for s sub k. And then plus, this is just going to simplify to k. So I have k plus 1 times k. I need a common denominator, so I'm going to multiply this by 3 over 3. And then I can add these together, and I'm going to factor out a k as well. So I've got k times k minus 1 times k plus 1 plus 3 times k plus 1 all over 3. And if I'm going to skip a couple of steps here just to expedite things. If I FOIL this out and distribute over here, what I'm going to end up with is k times k squared plus 3k plus 2 all over 3. If you want to go through and figure that out, you can. And then on this side, if I simplify all of this stuff, I'm going to get k times k plus 1 times k plus 2 over 3. All right, and then I could do one more step here. I can factor that numerator, so I'm going to get k times k plus 1 times k plus 2 all over 3, which is in fact equal to k times k plus 1 times k plus 2 over 3. So that checks, and we have proved by mathematical induction that this series here is equal to this expression here. Okay, I know I went through that quick, so if you have any questions, make sure you ask. That'll be it for this video, and we will see you in the next one.